Hello everybody and welcome. Thank you so much for joining me here today. In today's video, we are talking about the power of a point theorems. These theorems have to do with circles and secant lines and chords and tangent lines and their intersection points. Okay, that's why it's called power of a point, because it has to deal with the point of intersection. These theorems deal with the angle that is formed at the point of intersection along with the links of the corresponding secant line or tangent line or chord. This is another look at the formulas that arise. I feel like this is a little bit easier to look at, so feel free to pause the video and look at these formulas. But with that, let's dive right into it. So before we just go in and talk about the power of a point theorems, we need a little bit of background information. So first, I want to talk about how does a tangent line interact with our circle? And so if you're unclear, a tangent line is a line such that it just barely touches the circle. So it doesn't go through the circle like a secant line, it just barely touches the circle at a single point. So if we have a radius that intersects our tangent line, what angle is formed? So you might have heard in your math class, or you might just be looking at the picture and thinking it, but the angle formed is a right angle. And how do we know that this is a right angle? How could we prove this? And the way we prove this is something called a proof by contradiction. And a proof by contradiction is where you take your statement. In this case, our statement is that the radius intersects our tangent line at a right angle. And we take that statement and we assume it to be false, okay? And then we go down the line of thought of a direct proof, and then whenever we run into a contradiction, whenever we run into a piece that doesn't make any sense, we say, wait, this is a contradiction, this cannot happen, therefore my original statement of saying that this is not a 90-degree angle must be false, so it is a 90-degree angle. So let's go ahead and do that. So if we're assuming that this radius is not a 90-degree angle, then that implies there must be some line that extends from the center of our circle, which intersects our tangent line, that is a 90-degree angle. Okay, so let's say that position is just right here. Therefore, we're saying, hey, this angle is a 90-degree angle. Now, why is this not possible? Why does this make no sense at all? Well, notice that our yellow line is a radius of our circle. And notice that our purple line is a radius plus a little bit extra. Well, we know that the hypotenuse, the longest side of a right triangle, is always opposite our 90-degree angle. The side opposite our 90-degree angle here is our yellow side. However, our purple side is longer than our yellow side. And we know that, well, because we can physically see it. Our purple side extends past the outside boundary of our circle. And this is a contradiction. Therefore, we know that it's impossible for the angle to be 90 degrees at any location other than where the radius intercepts the tangent line. So that's how we know that the radius and tangent intersection forms a right angle. Moving forward, let's talk about the relationship of two tangent lines intersecting. Okay, so let's draw the point of intersection of each of these points. So we have 3 points that we're looking at. Here, let's draw in our radius intersecting each of our two tangent lines. Now we know that these lines form 90-degree angles. And let's draw in a third line connecting our center to our point of intersection. And so notice that these two triangles share a hypotenuse. This dotted line is the hypotenuse for both of these triangles. And also notice that they each have a yellow line of radius, okay, which is shared. We know our yellow lines must be congruent with each other. Therefore, by the hypotenuse leg theorem, these two triangles are congruent. Therefore, by CP/CTC, by congruent parts of congruent triangles are congruent, we know that these purple segments, the segments I'm labeling X and Y here, must be congruent. Okay, so this tells us that the section of our tangent line, which goes from that intersects with the radius to intersecting with the other tangent line, our point of intersection, point P, is the same length, is congruent to that same distance in our other tangent line. So this will come into play, and this is our first power of the point theorem. This is the intersection of two tangent lines. Let's also quickly talk about this relationship between a tangent line and a chord. Okay? This relationship will come into play whenever we are talking about a future relationship. So let's talk about it now. So I want us to pay attention to this angle here. And let's see if we can draw a relationship between this marked blue angle and another angle in our picture. So to get started, I'm going to draw a radius to the other two vertexes of this triangle. And so notice that we just formed an isosceles triangle. These two yellow lines and this long blue line, this chord here, represent an isosceles triangle. So we can say that this angle here and this angle here are congruent with one another. And what else can we say? Well, if I'm just looking at the picture, I know that my purple angle that I just marked, my purple angle plus that green angle, it must equal 90 degrees, as this is an intersection of a radius and a tangent. Also, notice that my central angle must equal 180 degrees minus my two green angles. And then also notice that the original angle in question is an inscribed angle to my central angle. And recall that an inscribed angle is half the value of a central angle. Therefore, my inscribed angle is going to be half of my yellow angle. So it will be 90 minus a single green angle. Now notice from this top equation that if we subtract the green angle from both sides, we will have that our purple angle is equal to 90 minus our green angle as well. Therefore, we can say that our blue angle is equal to our purple angle. And this is the relationship between a tangent line and a chord. It's also called the alternate segment theorem. And again, it's just stating that here, let's erase these extra lines that we don't really need. It's stating that these two angles marked, the blue angle and the purple angle, are congruent with one another. So let's just notice and appreciate this relationship, and we're going to use it in just a moment. Okay, now we're on to power of a point theorems. This is the chord-chord intersection. So let's talk about the relationship. So the chord-chord relationship, we're looking at this angle here in white, and we want to relate this angle to the two arc measures that are formed from the intersecting chords. So this arc measure that I'm highlighting in blue, and this arc measure which I'm highlighting in this purple color. Okay, I'm also going to go ahead and draw in some connections, making these into triangles. So I want you to notice that this angle here is an inscribed angle. These two angles are inscribed angles to my blue arc measure. And these two smaller angles are also inscribed angles, but to the purple arc measure. Okay, so I'm going to change colors here to a red. Let's talk about this third angle. What is the value of this third angle? Well, this red angle is equal to 180 degrees minus my blue angle and minus my purple angle. And my white angle is equal to 180 degrees minus my red angle. It's minus my red angle, but my red angle is 180 minus my blue minus my purple. Okay. And so if we simplify this, we can see 180 minus 180 is 0. A minus times a minus blue is a positive blue. And a minus times a minus purple is a positive purple. So we can see that my white angle is equal to my blue angle measure plus my purple angle measure. Now, how does this relate to the arc measure? Well, recall that your arc measure is congruent with your central angle, and your central angle is twice that of your inscribed angle. So what does that tell us? That means if we make a marking of our central angle, then our central angle here will be 2 of our blue angles, and similarly, our central angle to our purple arc will be 2 of our purple angles. Okay, so what I'm going to do is just scale up this. I'm going to say 1/2, and then I'm going to say, instead of blue plus purple, 2 blue plus 2 purple. But again, 2 blue and 2 purple is equivalent to the arc measure. So we're just going to say it's going to be 1/2 times the blue arc plus the purple arc. And there we have it. So this is the relationship between the angle that is formed by the 2 intersecting chords and the respective arc measures. Fantastic, fantastic. Isn't that beautiful that this just comes out of it? All, a circle and a bunch of triangles. It's just so cool. So cool. So this is the relationship between the angle that's formed in the arc measure. But what about, we had that second relationship, right, with the segments of our chord. So let's see what that relationship is. Okay, so here we have our 2 triangles. And again, let's refresh that this purple angle and this purple angle are inscribed angles to the same sector. Therefore, they are congruent with one another. And similarly, this angle here and this angle here are inscribed angle measures to the same arc measure on this side as well. This tells us what? This tells us by angle-angle similarity that these 2 triangles are similar. And what does it mean for 2 triangles to be similar? Okay, well, recall that if 2 triangles are similar, it means that their side lengths are proportional. Okay, their side lengths are proportional. Therefore, let's call this point P. Let's have a point A and a point B on the same chord, and a point C and a point D on the same chord. This tells us that our length AP is to CP as DP is to BP. And then we can cross multiply to get that AP times BP is equal to CP times DP. Beautiful. And all of this arises just because these triangles are similar. I just think that's so cool. And what's the use case for this? Well, if we're solving a problem and we're told something like AP has a length of 7 and BP has a length of 4 and DP has a length of 2, and we wanted to solve for CP, we would just say, well, 7 times 4 is 28 and 2 times 14 is 28. Therefore, CP is equivalent to 14. Fantastic. So this was two chords intersecting. This is the chords power of a point theorem. But what about the secant? What's different whenever two secant lines intersect? It's very similar, but it's a tiny bit different. So go ahead and pause the video and see if you can figure out the difference on your own. Here, I'll get you started just a tiny bit. Again, we're talking about this white angle in question and how it relates to these two arc measures, this blue one here and this purple one here. This is what we want to figure out, how this angle measure relates to these two arc measures. And I'm going to go ahead and help you out just a tiny bit more in that here are the two triangles that we're going to draw. So go ahead and pause the video and see if you can figure out the relationship between the marked white angle and the two arc measures. I'll give you a couple seconds. Okay, so let's get started. I'm excited for this one. So where is the inscribed angles for the blue arc measure? Well, it's right here and right here. These are the two inscribed angles for the blue arc. What about the purple arc? Well, the purple arc, it's down here and right here. Okay, so we want to relate our white angle measure to these arcs. Okay, and our white angle is in a triangle, but we need to know what this red angle is before we can define what our white angle is. So notice that our red angle is supplementary with our purple angle as it forms a linear pair with it. Therefore, our red angle is equal to 180 minus our purple angle. And our white angle, therefore, our white angle is going to be equal to 180 minus our blue angle minus our red angle. So we're going to put our red angle in parentheses, and that's going to be 180 minus our purple angle. Okay, if you're wondering why our white angle is 180 minus our blue minus our red angle, again, this in parentheses is our red angle. If you're wondering that, that's just because a triangle has a total angle measure of 180 degrees. And so therefore, the total triangle is 180. And then if we subtract the blue angle and the red angle, then we'll be left with the white angle. So that's how we know what we've written down to be true. Now let's simplify this. We have 180 minus 180, which is 0. We have a negative blue angle, and we have a negative times a negative purple, which is a positive purple. Now I'm going to shuffle this around just to make it cleaner for us. We have a purple minus a blue is equal to our white angle in question. And notice how this is just a tiny bit different than our chord-chord intersection. In our chord-chord intersection, this was a plus sign, and here it's a minus sign. And that has everything to do with the fact that the point of intersection is outside our circle. If the point of intersection is outside the circle, then we're going to have a minus sign. If it's inside the circle, like our chord-chord interaction, it will be a plus sign. So that's the difference between the two. Now we're going to do something very similar. Again, we have our white angle in terms of our purple and blue angle measures, but we want it in terms of the arc measure. So we're going to scale it up by a factor of 2 and then divide by 1/2 so that we can say that our white angle is equal to equal to 1/2 times our purple arc minus our blue arc. And there we have it. And so notice that whenever the point of intersection is outside the circle, you're always going to be subtracting the smaller arc from the larger arc and then dividing by 2 in order to find the angle measure. Next, let's talk about the segment relationship. So again, we're going to have a couple triangles. Notice that the point of intersection angle is shared in both of the triangles in question. And we also have this icy blue and this icy blue going to the same inscribed angle. Therefore, by angle-angle similarity, these triangles are similar. So we can say that their side lengths are proportional to one another. And if their side lengths are proportional to one another, we can write these relationships. So again, I'm going to call the intersection point, point P. I'll call this point, point A, and this one out here, point B. This point C, and this point D. And now let's write the relationship. We see that A times P is to C times P, as B times P is, as D times P is to B times P. Then we can cross multiply to get that A times P, or AP times BP is to CP times DP, as these are all, line segments. Perfect, perfect, perfect. The last power of the point we're going to talk about is how a tangent and a secant, what is their relationship whenever they intersect? Okay, and this one, it's solved the exact same way the secant-secant relationship is. So we know that this angle here in white, this white angle is going to be equal to, here let's mark these arc measures. It's going to be equal to 1/2 times our purple arc minus our blue arc. And I'll leave that as an exercise to you to solve. But I did want to point out the similar triangles here. Here, the two similar triangles is this big, large Kahuna triangle in question, and then this smaller triangle on the right-hand side. So think back to that tangent chord relationship I showed you, in that the alternate segment theorem, in that this angle must be congruent to this angle. Therefore, again, by angle-angle triangle similarity, these triangles are similar. Therefore, their side lengths are proportional. So if we call this intersection point, point P, this point A, this point B, and this tangent point C, what do we have? We have that AP is to CP, as CP is to BP. Therefore, AP times BP equals CP squared, equals CP times CP. So this is why the tangent-secant intersection is a little bit different than the secant-secant. It's because there's only one point of intersection, and the side length CP is shared in both of the similar triangles in question. So here is the tangent-secant relationship for the power of the point theorems. Now let's go on to some practice problems using these relationships. Okay, so here we are solving for x. Feel free to pause the video and see if you can solve this problem on your own. I'll give you a couple of seconds. Okay, excellent. So here we are solving for x. We know, what do we know here? Well, we know that this point in purple, this purple angle, is going to be equal to 1/2 times x plus 110. Our point of intersection's in the center, or in the middle of our circle. Therefore, this is a plus sign. Remember, with chords, it's a plus sign. And so we just want to solve for x here. But what is the value of our purple angle? Well, it's on a line with this angle marked 120 degrees. Therefore, it is a linear pair and supplementary with 120 degrees. Therefore, my purple angle is 60 degrees. And so now I just simply have to solve for x. What times 1/2 equals 60? Well, 120 times 1/2 is 60 degrees. Therefore, x must be equal to 10 degrees. Great job, great job. Next problem. Here again, we are solving for x. I'll give you a couple of seconds so you can pause the video and solve this problem on your own. Okay, so in this problem, we have two secant-secant relationships. We have the left-hand side, and that's this relationship, and we have the right-hand side, that is this relationship. Okay, and they're both secant-secant. So let me erase these lines, clear it up a little bit. And notice that this portion is shared in both the left and right hand side, and it is unknown. So let's call this unknown side y. And notice that we need to solve the left hand side first, because the right hand side has two variables. It has the x and the y, so we wouldn't be able to solve it immediately. So we need to solve for y first on the left hand side, and then we can go and solve for x. So we know that 5 times 5 plus 11 times 16 must be equal to 4 times, well, 4 plus y. And I don't really like thinking about this term as 4 plus y. I like to just think about this as 4 times what? And I know that I'm looking for this full section, and then I'll subtract 4 a little bit later. That's just how my mind works. So I want to show you how I solve these problems. So here I recognize what? Well, I know that 5 times 16 is the same thing as 5 times 4 times 4. And so this needs to equal 4 times something. But it needs to match on both sides. So what's missing is another 4 and a 5. And so I know this full distance is going to be 4 times 5, which is 20. And so therefore y must equal 16, as 20 minus 4 is 16. Okay, now I have enough information to solve for x, in that I have 7 times my unknown full length is equal to 5 times 5 plus 16, which is 21. So 21 is just 7 times 3. So this is 5 times 7 times 3. And so what needs to go in this box is a 5 times a 3. So a 15. So this full length is 15. Therefore, x must be equal to 8. Bam, bam, bam. Thank you, ma'am. X is equal to 8. Great job if you solve this problem on your own. Give yourself a pat on the back. Also, if you made it this far, go ahead and hit that subscribe button. I truly appreciate it. Now let's look at this next problem. Again, feel free to pause the video and solve this problem on your own. we are looking for the value of x. Okay, and here I actually gave you a little bit of a hint to start out. I intended the problem to look like this in the beginning. Those lines, we are going to bring them back and we're going to use them to solve our problem. Why are these lines so important? It's because we're recognizing that our triangle is flush with our circle. Therefore, all three sides are tangent, meaning all of these angles are 90 degrees. And then also notice that this central angle must match with our arc length, or our arc measure rather. So this central angle is 150 degrees. And then also notice with these drawn in radii, which are tangent, or which intersect with our tangent lines of our triangle, we just formed three quadrilaterals. Okay, we have three quadrilaterals here. And so here I'm paying attention to this quadrilateral. And notice that two of its angles are right angles, and a quadrilateral has a total of 360 degrees. Therefore, the opposite angles must be supplementary. They must sum to 180. So this angle in question must be 30 degrees. And if this angle is 30 degrees and this angle up top is 50 degrees, then the third angle of the triangle must be 100 degrees, as a triangle's angle measures sum to 180 degrees. Okay, next problem. Here we have a standard power of the point theorem question. Go ahead and pause the video and try to solve it on your own. I'll give you a couple seconds, or take a sip of my drink. Okay, so for this problem, we know that 10 times 10 plus 8 is 18, and this must equal this sum y squared. Okay, this tangent line. It's not marked, it's just some unknown thing, and it's y squared. But notice the right-hand side must also equal the y squared. So we can set the left-hand side equal to the right-hand side. So the left-hand side of 10 times 18 must equal 12 times 12 plus x. Okay. Now we can go ahead and solve. So how can we solve this problem? Well, 10 times 18 is 180, and it's going to equal 12 times 12 plus x, which if we distribute, we get 144 plus 12x, and then we can subtract 144 on both sides and have 36 equals 12x. We can divide by 12 to have x equals 3. Now there's lots of ways to solve this problem, so if you did it a different way, let me know down in the comments below. But what I just showed you is a perfectly valid way to go about this problem. Up next, we have another problem. So feel free to pause the video and solve it on your own. Okay. So this problem is arguably one of the easiest problems, and it's very similar to the previous problem in that the relationship is transitive. So since we have a tangent and a tangent, we know that x squared is equal to 5 times, well, we don't know this value. That's strange. So that's kind of messy. 5 plus some unknown value, we'll call it y. But hey, we know that this whole thing must also be equal to 8 squared. Well, therefore, we can cut out the middleman and just say x squared equals 8 squared. And so, hey, x equals 8. Bada bing, bada boom. You are done. X is simply 8. Excellent work. On to the next problem. We are looking to solve for x. As always, feel free to pause the video and solve on your own. But we're just going to dive right into it. We're looking to solve for x. So we know, what do we have here? We have two circles that are touching, and we have some tangent line. So we know that these are right angles. So what can we do to solve for x? Well, what we can do is we can draw a line that's perpendicular such that it creates some rectangle. Therefore, our dotted line also has a value of x, a length of x, and now we have a right triangle. So let's zoom in on our right triangle. So let's recreate it. Okay, so we have some value of x. What's this length? Well, this length here is going to be 25 minus 9, which is 16. And then what's the length of our hypotenuse? Our hypotenuse, well, we see that our radii in the smaller circle is 9. So this distance is 9. And similarly, this distance will be 25. 9 plus 25 is 34. So we know our hypotenuse is 34. Next, we can use Pythagorean's theorem of a squared plus b squared equals c squared. If we plug in values, we have x squared plus 16 squared equals 34 squared. Now let's go out to the side and see what 34 squared is. I don't know that in the top of my head. If you do, fantastic. 4 times 4 is 16. 4 times 3 is 12, plus 1 is 13. Put a 0, 12, carry a 1, 9, 10. And so it is 6, 5, 1, 1. So 1156 is 34 squared. So we have 1156 is equal to x squared plus 256. I do know 16 squared is 256. Now let's subtract 256 from both sides. And we get x squared equals 900. And we take the square root to see that x is equal to 30. So the value of x is 30. Fantastic work, everybody. On to the next problem. Here, let's just dive straight into it. We have some radius that is 3. So we know this diameter here must be 6, as our diameter is twice our radius. We have a secant and tangent line intersection. Therefore, we know that 2 times 2 plus 6 is equal to x squared. 2 times 2 plus 6 is 2 times 8, which is 16, equals x squared. Therefore, x equals 4. Great job. On to this next problem. Now I'm going to go ahead and tell you this problem is arguably the hardest problem. So if you want a challenge, pause the video and see if you can solve this problem on your own. Okay, let's dive right into it. So we have two variables here. Which variable do we need to solve for first? Typically I go in alphabetical order, but in this case, it's a tangent and a secant intersection. And we have two variables on our secant line. Therefore, we won't be able to solve for it first. We need to solve for y first. And for y, we have a chord intersection. So we know that 4 times 9 must be equal to 12 times y. Okay. We know 9 times 4 is 36. And we know 12 times, so we can divide by 12 to get y is equal to 3. 12 times 3 is 36. Excellent. So we know that y is equal to 3. Now let's, I won't erase this, but I'm going to shrink it down just in case we need some extra room. Here we go. I'll put it over here. Now let us solve for x. So how do we solve for x? Well, we know that 18 squared is going to be equal to x times x plus 15. So 18 squared is 324. And this will equal x times x is x squared. And x times 15 is plus 15x. Now we want to subtract 324 from both sides and set this equal to 0, such that we have 0 equals x squared plus 15x minus 324. And now we want to factor this. And we can factor it two ways. We can look for items that multiply to give us 324 and sum to be 15. Or we can use our quadratic formula, negative b plus or minus square root of b squared minus 4ac all over 2a. I'm much more down to factor. And let me show you how I look for factors. So I'm looking at 324. I want to know things that multiply to give me 324. Well, we already know that 18 and 18 multiply to give 324. And then from here, we have a 6 and a 3, and a 6 and a 3, and a 2 and a 3, and another 2 and a 3. And here, let me move this up a little bit. So we're going to move this up. There we go. And so what am I looking for? Well, I can just look at my prime factors. My prime factors here are what values? I have a 3, a 3, I have 4 3s and 2 2s. So this is what I'm paying attention to. And I notice that, hey, well, 3 times 3 times 3 is 27, and that will leave me with 2 times 2 times 3, which is 12. And so 12 and 27 multiply to give me 324, and that sums to 15. So perfect. That wasn't so bad. So I have 0 equals x minus 12 times x plus 27. Now I know my solutions are x equals positive 12 or negative 27. And as x is a length, it must be positive. Therefore, x is equal to 12. If you got this one on your own, give yourself a big pat on the back. Doesn't get any harder than this one. So fantastic job. Moving forward to one more problem. Here we have a quadrilateral and a circle inscribed within, and we're looking to solve for the value of x. Now there's an easy way and a hard way to solve this problem. So let me show you the easy way, because who wants to solve a problem the hard way? So remember that when two tangent lines intersect, those intersection points are congruent. And what do I mean by that? Well, let's mark all the tangent points. So this portion must be congruent to this portion, right? And we can do that all the way around. This portion must be congruent to this portion. Same here and same here. So we could do a lot of workaround math to solve for what x is, or we could notice that, hey, our two opposite sides, 36 and 42, our two opposite sides, 36 and 42, they include a side length with 1 marking, a side length with 2 marking, a side length with 3, and a side length with 4. And our other opposite sides are similar. They have a side length marking of 1, 2, 3, and 4. Therefore, our opposite side lengths must sum to be the same value. So 36 plus 42 must equal 40 plus x. Therefore, we can see that 78 equals 40 plus x, and so x is equal to 38. Fantastic job. Great work, everybody. Thank you for joining me for this Power of a Point Theorems video. If you're new here, hit that subscribe button. Hope to see you in a future video. Until next time.